Hello, welcome back to part 6 of our data science series on linear regressions. Okay, and this is just a series of the videos we're going to do devoted to linear regressions. Okay, what we're working on right now is the error measurements for the slope and the y-intercept. And we've already measured some error measurements over here based upon the predicted y and the actual y. But now we're going to do some error measurements on the slope, which are these, and then some error measurements on the y-intercept. Okay, so let's go ahead and get started. This is what we call the standard error. Just a second, and let's cut over. Here it is, the standard error of slope. Okay, and we say say this as SE sub m. M means the slope, or you could just say it's the SE for the slope, whatever. But how do you calculate it? Well, it's the root mean squared error for the y, for the predicted y, divided by the square root of the x minus the mean of x squared summed up and then square root. All right. Down here I just said SE sub m is also known as m SE, so you can call it whatever you want. This is important. The lower the better. With most error measurements, the lower the better, because you want less error. Okay, so let's go back to the spreadsheet and let's look what we got. So here we got the formula, and now it's set up as K7, which is the RMSE, and we're dividing by the square root of F5, which is the delta x mean squared, which is what we showed before. So let's go ahead and uncover that. Now, it's important when you look at this to look at the magnitude of the number. So for example, we're predicting that the slope is 3.63. Okay, in fact, let me take off some precision. That's just way too much precision. All right, we're predicting that it's that, and this is kind of like a standard deviation for that prediction. So let me take some precision off. So what this means is like 3.64 plus or minus 1.14. Okay. Now, in reality, inside this guy's brain, inside of his head, the sensitivity is 3. The slope should be 3. But based on his behavior, which is all this data down here, we estimated it was 3.64 plus or minus 1.414, which puts us right in the range. Okay, 3 is definitely in the range of 3.64 plus or minus 1.14. Okay, now if you go back to your, if you did see it, there was a video on normal distribution. Okay, the SE for the slope is essentially a standard deviation. Okay, which means that the true sensitivity has a 68% probability of being within the estimate plus or minus 1 standard deviation. Okay, and if that doesn't mean anything to you, go back to that video and watch that video on normal distribution. It also means that the coupon sensitivity has a 95% chance or probability of being within the range of the estimate plus or minus 2 times the standard deviation. Okay, so there you go. That's kind of how we use this SE standard error for the slope. It's a standard deviation for the slope. Okay, the next thing we're going to measure is called the t-value. Okay, and the t-value is nothing more. It's really simple. It's taking it's a way of normalizing the error. Okay, and how we do that is we take the slope here and we divide it by the error. Okay, and basically what this means is how many amounts, or divided by the standard deviation. I apologize. Take the slope divided by that standard deviation for the slope, and that's saying how many standard deviations of that slope fit within the slope. If you have very little error, the standard deviation will be very small, which means you can fit a lot of them inside the slope value. So bottom line, the t-value, the higher it is, the better. Okay, and let me show you this. This is the t-value, the slope divided by the standard error. And so I probably should put this, this needs to be, that needs to be subscripted. I apologize, we're fixing this in real time. Bingo. So the t-value of the slope is equal to the slope divided by the standard error of the slope. Okay, and it's also called the t-ratio. And for this, the higher the better. And think about it. If the standard error is low, or the standard deviation is very low, that makes the t-value higher. And so that means the higher the better. Okay, so if we go back to our spreadsheet, and here it is, it's I7, which is the standard, the estimated slope divided by the standard error in M3. And so let's calculate what it is, or uncover it, excuse me. And too much precision there, so let's take that off. 3.19, and that's not a bad number. Okay. Typically, you're going to want t-values 3 or more. You might think of a t-value as a kind of like a z-score, and if it's I don't know how to say that. No, forget that. That'll get confusing. I see it in my head one way, but I'm not sure how to explain. It's kind of the inverse. But the thing is the higher the better. If it's above 3, it's pretty good. Okay. If it's like above 10, you're rocking it. If it's above like 40, man, you're acing it. So, yeah, you want it to be, if it's below 3, if it's below 2 or 1, then it's becoming very questionable. And the way I know that is because of the next variable that we're going to calculate, which is called the p-value. So if we go over here, let's talk about the p-value. All right, so the p-value is a really strange variable that a lot of people just don't understand. And trust me, I've been doing this for many years, and even still to this day, it's one of those kind of things that you wrestle with trying to understand. All right, what is p-value? Well, p-value is essentially the probability that the null hypothesis is 0. All right. That tells me nothing, right? What is that? What is the null hypothesis? Think of it this way. I'm estimating what? I'm estimating, if I go back to, well, I'm estimating the slope. In this case, I estimated it to be 3.64, okay? In reality, it's 3, but I'm estimating it as 3.64. Now, remember, I'm trying to figure out what's inside this guy's brain. Let's say that what's in his brain is really 0. That would be the null hypothesis. The null hypothesis says that what's in this guy's brain, the true sensitivity is 0, okay? And then what we're going to do is we're going to calculate the probability that that is true, that what's really in this guy's brain is 0 based upon the estimate that we have, okay? All right, so let's say I had, well, to do that, what we need to do is look at the error and the ratio of what we estimated versus the amount of error that it has, and that is the t-value. The higher the t-value, the less probable that the null hypothesis is true. Okay, so In other words, the more probable that my estimate is accurate. Okay? So, to do that, what we do is the following. We take that t-value m, and let me go ahead and subscript that, just to make it more accurate. We're going to take that t-value m, and we're going to also put in what we know as the degrees of freedom, and we're going to do two-tailed t-table lookup. What that basically means is we're going to take the value, that t-value, and we're going to put it in, we're going to look at it here, and we're going to correlate it with the number of degrees of freedom that we have, and then at this top rail that says two-tail, we're going to find the number up there that matches between the row of the degrees of freedom and the value of the t-dist, or excuse me, the value of the t-value, the t-value. Now, in this particular case, the t-value was 3.19, okay? So, and my degrees of freedom are like 82. So, if I go over here, look at this. If you look at this, these numbers just get lower and lower as I go on. In fact, I only got down to 30 degrees of freedom. So I'm kind of screwed there. And plus, you can't see everything because you are looking at my face instead of the table. Well, let's put my face over here and make it big so you can see my face. And if we go back over here, notice that as the degrees of freedom increase, the t-value goes down. Okay, so already here, our t-value was 3.19 from the spreadsheet. Here it's already lower at 30 degrees of freedom. I need to go to 82. It's already lower than what I need. So chances are I'm going to have to go to this here, 3.19, and look at this. At 30 degrees of freedom, it's already 3.3. I'm going to make the assumption, and I don't have all the data here, but if I go to around 82 degrees of freedom, that's going to bring me pretty close to 3.19, okay? Which means that this value right up here, oh, you can't see that, can you? Let's bring this over. Actually, let's go over here, shift the whole thing over. There we go. So, like I said, this at 30 degrees of freedom, this is 3.3. If I go all the way down to 82 degrees of freedom, chances are it's going to be fairly close to 3.19 or maybe 2 point something. Bottom line is on this table, the closest thing that's accurate in the two-tail test is 0.002. What that means, we're estimating the slope. In fact, let's go back to the spreadsheet. We're estimating the slope to be 3.64, which is right here, okay? Now, in reality, it's 3. So I want to figure out with the p-value, what is the probability that in reality this is 0? And to do that, we go through that formula, and here's that formula again. It's equal to t-dist, and then this is the t-value, the degrees of freedom, and then 2 means a two-tailed test. But what that does is it tells me a probability figure. Now let me uncover that to see what it came up with. It came up with, oh, check that out. Isn't that really close to 0.002, which we saw on the table? Well, it is. What this means is about 2 times out of 1,000 experiments that I would run, where the real sensitivity was 0, would I ever get an estimate that was as high as 3.64? What that is saying is that 3.64 has a 98% probability, 2 out of 1,000, that's a 99.8% probability of being within the range. Okay? I shouldn't use that. What it's really saying is that there's a 0.2% probability that it's really 0. Okay, that's more accurate. Okay, and let's just stick to that. This is important. From a scientific point of view, it means a lot. We're going to go ahead and end this right here. Start the next video right now. We'll go to part 6.